Welcome back, LeetCode extraordinaires. Today is day 26 on LeetCode every day. Yesterday we did mostly review. I did a lot of review on problems, and I think there's something to reviewing problems. And I think someone said, or the guy, I think in the book called Training Bobby Fischer, he mentions that the greatest determinator of if a player will become a grandmaster is not how many games they've played or who they've played against, but in fact is how much time they spent poring over their old matches. I think the intuition behind that is that there's a lot more to learn in the mistakes we've already made. So I think there was a lot to reviewing the old problems, and I find that I get a lot out of reviewing the old problems. So yesterday was just mostly review. I said I was going to do insert interval. We didn't do that, and I said I was going to do Lru Cache. Still haven't done that. I think I'm technically avoiding Lru Cache because it's a hard problem, but I think that's partly because I got used to doing easy problems. Now that the difficulty is ramping up, I'm having some trouble psyching myself to do the hard problems, but it is what it is. So we'll do Lru Cache first today, probably. No, I'll do some review problems first just because I think it's better to get into the practice, like getting into form with the review problems. And then by getting the form, like making sure you read the entire problem description. I don't jump the gun. I make sure I double check the constraints, make sure I write pseudocode first and then write the code, stuff like that, so that when I go into doing new problems, I'm already in good form to do those problems. That being said, we're still doing an hour and a half, and there could be some improvements there, but sometimes I think someone has said this, I don't remember who, but sometimes you have to run a shorter distance that you can keep running. So I wanted to do 2 hours, but 1 hour and a half is kind of all we have in the bucket. I also think there was something else I was going to do, or like I'm also noticing that and I'm tending to bounce around too much in terms of what problems I'm actually doing. But I think we're settling in using the grind 75 alongside the review problems. So I think today we'll aim for we'll do some 2 review problems. So maybe 40 minutes of review and then 40 minutes of new problems. And in that case, I'm hoping to do insert intervals, which I'm pretty sure I know how to do pretty quickly. So we'll do that one just to knock it off the grind 75 list, and then we'll finish Lru Cache, and then we can keep moving forward. That being said, make sure to join the Discord, the Hyperbolic Coding Chamber. It is absolutely jumping. There are thousands upon thousands of people inside the Discord. Yeah, also I noticed one more thing I've noticed with the last, I would say just particularly with today's session and maybe another session this month, I've noticed it's only been like maybe 2 out of 30 times or something like that, but I've noticed I've had to sort of dangle rewards for myself at the end to make sure that I do the time required to get better. I think that's just something that comes with trying to do something every day, but I do think it cheapens the process. I think many people who have done some pretty cool things use that method, but I think they've also always said, and I think you can see it as well, that you're sort of trading a piece of yourself for the outcome. So for example, if I'm trying to do my time today, if I say that I'm going to do something afterwards, then it kind of lets you get through today. But the problem is you can't keep abusing that tactic, because then you have to keep raising the stakes. The thing has to be better and better so that you can continually psych yourself to do the activity. So that doesn't scale long term. I also don't think you get any of the executive function benefits by doing that, because then you're kind of just abusing the reward system. That being said, I think there's something to doing something you don't want to do, particularly with no reward at the end, just because it kind of forces you to do it anyway. And I think, from what the book people say, apparently that increases your executive function, planning, and all that stuff. So I've noticed that to be the case when I forced myself to do gym stuff or something like that. I also think it also depends on exactly what you're doing. So, for example, in the gym, you might be doing a slew of different exercises, but you don't really necessarily have your focus on one thing throughout. Generally, your attention is wandering through music or a podcast or the exercises. But I feel like if you're just doing one thing. Like when you're focusing on this LeetCode thing, you're kind of focusing your mind on this one problem. And the kind of aspect of learning to focus your attention on one thing, I think, has been proven to increase executive function and planning and delayed gratification, all the things, stuff like that. That being said, 1 hour and 30 minutes, since I'm gonna raise the stakes to do 1 hour and 35 minutes, just because I can sense that I don't want to do 1 hour and 35, so just to push the bar a little bit, but we're just gonna jump into it. I'm gonna do 40 minutes of random problems just to get into form, and then we'll switch to insert interval and Lru Cache to move forward. That being said, make sure to join the Discord, and I'm just gonna jump into it. So we have number of islands. We've done this problem a few times. So you have grid, which is a parameter into the function. We're getting a matrix of strings, and we're returning a number. Given an m by n 2D binary grid, which is the input to the function. Input into the function, which represents a map of ones, land, and zeros, water. Return the number of islands. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. You may assume all 4 edges of the grid are surrounded by water. So this is our m by n matrix. We have 4 rows, and it looks like 5 columns. It looks like these can vary, but it looks like we are given this grid, and they're saying ones represent land and zeros represent water. Return the number of islands. So this output is 1, and it's 1 because we have a group of ones. We have 2 groups of ones connected by this one here, which gives us 1 island, since they'd all be connected horizontally by this 1, 1. Example 2, we have 3 islands. We have 1 group of islands here, 1 here, and 1 here, and none of them are connected by adjacent or vertical ones. So they actually produce 3 separate islands. So I think what we can do is, if we visualize this m by n grid as a graph, we could do a depth first search where a 1 would trigger a, so let's just write it out. We could have islands, and we could iterate over the grid. So we just iterate over the grid, we iterate over the rows, and then iterate over the columns. The goal of this would be to find a 1. If matrix C equals 1, then we know that we found the start of an island. If the start of the island exists, then we could increment islands, right? And then we could clear the nearby islands. So if we do that, the depth first search would check all adjacent ones and make sure that they it would pretty much try to clear out this entire island so that we don't want to keep re-triggering this depth first search. So the goal with that would be, like, if we have 1, we'd find this 1 here, we trigger the depth first search, right? We want to check up, down, left, and right because of the rule they gave us. The island is surrounded by water. It's formed by connecting adjacent lands horizontally and vertically. So we'd find this 1 here, and maybe our order would be, we'd go up, right, left, down. So for 1, we would go up and be like, oh, it doesn't exist, and we'd go right, right? We'd find another 1, right? And since we want to clear islands, we actually want to turn any valid matrix C that's a 1 to a 0. So we turn this to a 0. There's nothing above us. Go right. This is a 1, so we turn it to a 0. There'd be nothing. We'd go above us. There's nothing above us, so we go right. Turn this to a 0. Check above us. There's nothing. We go right. There's a 0, so we ignore it. Right. Then we would go down. See that 1 exists. We turn this to a 0. we check above us, which is already a 0, right is already a 0, down is already a 0, and left is already a 0, so we pop this off, go back here, right, down was a 1, which is our 0 now, left is also a 0 now, because we were just here, then we'd go back to here, right's a 0 now, down's a 0, left's already a 0, right, down's already a 0, down's not a 0, so we'd go down, then we check up, 1 is already a 0, 0 is already a 0, we'd go down, right, we go back to this one, check up, 1 is a 0, right is a 0, down is a 0, left is a 1, we check up and around, right, 1 would still exist here, so we check above it, it'd be a 0, right would be a 0, down would be a 0, left doesn't exist, we pop back to this one, check, right would be a 0, bottom is 0, 0, left is out of bounds, pop back to this one, left is a 0, up is 0, pop back, pop back, pop back, and we would continue iterating, right, just from that first one, we'd have cleared out all the zeros, and then we'd still have to complete the n by n operations, and we'd get an island equals 1. So basically an island equaling 1 starts a depth first search. So I think we could implement this. And for the second example, this also works. If we check 1 here, that would start our depth first search, which would clean the island or clear the island. This would change to 0. We'd go right. We'd go up, it'd be out of bounds. Go right, it'd be a 1. We change to 0. Go up, out of bound. Right is a 0. Go down. Change this to a 0. Go up, it's a 0. Right's a 0. Down's a 0. Left's a 1. Go back to this one. We go up, it'd be 0, 0, 0. And left would be out of bounds. So we clear all these zeros. We'd pretty much skip all these because the depth first search only starts when a matrix equals 1. And then we'd keep going. And then from here, we'd start another depth first search. We'd check all around us. We'd turn this 1 into a 0. Check up, right, left, and down. They'd all be 0. So we'd keep going. And then we'd find this one, which would increment islands. And we'd have 3 islands, all of them cleared out. So I think we can implement this. Say islands equals 0. Or let row equals 0. So to iterate over the matrix, we'll just do iterate over the length, which would be the number of rows, and then for each specific row, we'll check the length for the column. So row is less than grid dot length, row plus plus, and then we can duplicate this, slide it over, and this will be the columns. And the column is going to depend. The column length is going to depend on which row we're in. We'll do col plus plus. And so from here, we want to iterate over the columns, which is what we're doing, right? And then we'd say if the matrix equals 1, so we can just uncomment this line, right? How do we get the matrix that we're at? The matrix that we're at is going to be grid sub row sub column, and it's not if it equals 1 as a number, because these are actually strings. And we see that m can be up to grid length, n equals the length of the column, how many columns there are. You have to subscript the row and get that column. We know that there's always at least 1 row and 1 column, and that all the elements in the grid are either a string of 0 or 1, so we have to make this one a string. And we do islands plus equal 1 because we found at least 1, 1. And we want to call clear islands. Clear islands, to do a depth first search, is going to require reference to the matrix as well as the particular row and column that we're in. It's going to take 3 parameters: the row, the column, and the grid, and we want to make sure that we only call clear island for a matrix that is a 1. So we don't want to call it if it's not a 1. That being the case, since we found an island, right, we know that the current index we're at is actually a 1. That being the case, right, we'd want to change that current index to a 0 because we never want to visit it again. At the same time, we want to make sure that row and column are valid indices, is a valid matrix in the matrix. To do that, we could just use safe navigation operator. So we could just say grid sub row, right, sub call. And I guess we could just say if that's not the case, we can just return, right? And then we're going to do 4 calls, right? Because we want to do up, down, left, right. And so one way we can, before we call that, we just want to make sure that the indices actually equal 1 before we do that. And if we want to do that, we can say row sub call like we did above, right, equals 1. If it equals a 1, then we'd like to actually call a depth first search for that matrix. But to do up, down, left, right, this row and column is actually the index we are at currently. So to do up first, we'd actually increase column by 1, and then we could call clear islands grid row call plus 1. Duplicate this 3 times, and we're going to do up, down, left, which is going to be row minus 1 for both of these, and in front of us will be row plus 1. So make sure these match. The current row wrap up 1, the current row wrap down 1, the current row wrap behind us. So this is actually wrong. It should be there. So row minus, and then in front of the row wrap, it's the right side. So this is actually not up, down, left, right. This is up, down, left. It's up, down, left, right, but not the up, right, left, up, right, down, left that we used earlier. But any order is fine. So I think this makes sense. So to check that, we could run it really fast. So we're iterating over the rows and the columns so the row for the particular grid that we're at. To get the column length, we subscript the grid row. The index would get 0, we get 5. So call would start at 0 and go up to 5 columns. Does this grid 0 sub 0 equal 1? It does. We'd add 1 to islands. We want to return the number of islands. And then we want to clear the local islands. So does this grid exist? It does. So we wouldn't return. We'd set it equal to a 0. Then we'd check if grid sub row sub call plus 1 exists. It does not, so we wouldn't call that. Does grid sub row sub call minus 1 equal 1? It does, so we would call depth first search for that, change it to 0, push a call of clear island onto the stack, for which we would check if the row exists. It does, we set it to 0. Then we check if above it equals 1. Above it does exist, but it doesn't equal 1. Then we would check below it. If below it equals 1, it doesn't. Then we check to the left of it. Left of it doesn't exist. Does the right of it equal 1? It does. Change that to 0. Push another call onto the stack. We check if above it equals, we check if it exists. It does. Change it to a 0. Check if above it equals 1. It does, so we call depth first search for that. Change that to 0. And we check down, left, right. All of these would be 0. Pop back to this one, this one, this one. So all these would be set to 0, and then we could keep iterating. So I think this makes sense. Line 46. Given if Looks like we're missing bracket. So it looks like this works. So this works. It looks like the time complexity would be m by n operations. Would it be m by n operations? Would it be n by n? We have to visit pretty much every node in the matrix because we're visiting every indice, so that makes sense. Would it be n by n operations? I think so. Space-wise, space-wise, we only do a depth first search. I want to say the space complexity would be the worst case is that I think the worst case, if the grid is all ones, it's not a worst case because on the first depth first search, we'll have done n by n recursive calls, so maybe that is the worst case. Let me see. Oh yeah, so space complexity is worth n by n. Okay, so the graph is filled with lands where the depth first search goes n by n deep. So we do a depth first search. It looks like there's another version. You can linearly scan the 2D grid map. A node contains 1, then it is a root node that triggers a breadth first search. Put it into a queue and set its value as 0 to mark as visited node. Iteratively search the neighbors of enqueued nodes until the queue becomes empty. Iteratively search the neighbors of enqueued nodes. So this looks like an iterative solution actually. With 3 minutes, I'll just use the 3 minutes to read the problem. Linearly scan the 2D grid map. If a node contains a 1, then it is a root node that triggers a breadth first search. So they check if the grid isn't empty. They don't need to because the grid always has at least one value in it. They need to know the number of columns for the grid to start. Iterating over the rows and the columns. If the matrix C equals 1, then we increment the islands. Then we mark grids of RC as visited. Then we create a queue of neighbors. We push RC onto the queue. While RC isn't empty, we'll take the first neighbor off. Oh, we'll get the first neighbor. We'll pop that same column off. And then int row equals RC.first, comma, call equals RC.second. What is RC.first and second? Neighbors.front. Oh, it's a queue, but it's a pair of tuples. Oh, so I guess row and okay, so it's just a tuple. It's just a weird C++ thing. So they check if it exists and if it equals 1, and they push the neighbors onto it and set it equal to 0. And then they do it again. If it equals 1, they'll push it on and set it equal to 0, and so forth. I see. So it looks like they're doing an inner while loop to do this. Okay. So you check if it exists and if it equals 1. If it does, then we'll push it as part of the breadth first search, because it would be handled in terms of a queue. that's the case, what does that look like? If you have 1, we'd set it equal to 0, then we'd push the neighbor, we push it onto the stack, onto the queue, then we pop it off, and we check if above it is inbounds, it's not, then we check if the right is inbounds, and it equals 1, well it is, set it to 0 and push it on to the queue to be processed later. Check if 1 is, but we push it onto the queue to be processed later. And then neighbors isn't empty, so we go to 1. I see. Let's see. I see. So we have 40 minutes of review still remaining. We have delete node in the linked list. This is actually relevant. It's actually relevant. This is actually relevant to insert to Lru Cache. But write a function to delete a node in a singly linked list. You will not be given access to the head of the list. Instead, you'll be given access to the node to be deleted directly. It's guaranteed that the node to be deleted is not a tail node in the list. Right, because we can't delete a node. We can delete a node in the linked list, but not if it was the tail node, because we can't change where this previous pointer is pointing, unless you were in like C++ or something. So example, they're giving us 5, they want us to linked list to be 419. If they give us 1, they want us to remove 1. Number of nodes in the given list is in the range. It's 2 to 1000. But if each node in the list is unique, node to be deleted in the list is not a tail node. So the way you could delete this node is just by, you're given the 1 node, you could just copy the next node's value into this node and then set your next pointer to this node's next pointer, which would be null. So that would work for this case. Copy 9 into 1 and then set 1's next pointer to whatever 9's next pointer was. The same thing works for 5. If we had 5, we copy 1 to 5 and set 1's next pointer to 1.next, which would be 9. So we could say root so there's at least 2 nodes in the list. So we'll just run if the root node exists. We'll say root.val equals next.val, root.next equals root.next.next. So root.next equals root.next.next. Oh. There's one way to delete a node. So a function is anagram. We have S and T. We have to return Boolean. Given 2 strings S and T, return true if T is an anagram of S and false otherwise. An anagram is a word or phrase. Anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all of the original letters exactly once. So return given two strings s and t, return true if t is an anagram of s. So if t is an anagram of s, and s is an anagram of t, so it doesn't really matter. So anagram and anagram are the same because they are comprised of the same occurrences of letters. So if we were to create a map of s, right, where the map's keys would be the letters in s and the values would be the occurrences, t would be a map that is basically symmetrical to s. So to test if two things are an anagram, that's how you can do that. Another way you can do it is by trading space for time. So the minimum prerequisite for an anagram is that they're the same length. So if s dot length not equal t dot length, then it's not an anagram. So you could do a version where you sort both strings. That would be s log s plus t log s. T log t in the worst case. And in that case, what you would do, if you couldn't use any space, you would just sort the strings in place and iterate over both of them to make sure that they match, or just check if they're the same string. Otherwise, you could create a map of values for s and then iterate over t, subtracting values from s. So iterate over t, right? Check if value exists in s map. If it does exist in the s map, iterate over t. Check if values exist in s map. If it does, decrement occurrences. Actually, I want to see if I can come up with a new solution. I'm wondering if we just take the ASCII values, since they all have different values, and sum them up. I wonder if that would give us the correct value. So we said s value is s dot to string, s dot to lowercase. Oh, they're both lowercase characters, so we can skip that. We could spread it into an array, and then if we did reduce a b, what if we did a dot car code at 0 plus b dot car code at 0. Do the same for t, and then we could return s value equals t value. This is expression expected on line 2. I think I just have one too many equal signs. Type number is not assignable to type string. So we have an array of characters. We reduce, we do a dot car code at plus b dot car code at. Both of these should be numbers that addition should be possible. Yeah, just slightly smaller, and we'll just do as number number is not assignable to type string. Type number. So it's like something is a number and it's being assigned to a string. Does it think that this variable is string? I don't think this will change anything. We have an array of characters. We reduce, we have an array of characters, and we do car code at because they're an array of strings. A and B would be strings. Then we add them with car code at 0. At index 0. Type number is not assignable to type string. Not seeing where the number is. Type number is not assignable to type string. Something is a string. Oh, the output of the reduce function has to be of the same type of the input. So I'm turning an array of strings. I have to produce an array of strings. Being the case, then we could just map. We'll just say car.car code at 0, and then we can, in the reduce, we'll just add them together. And I think that should make it go, I should make one of them go away. Okay, so that looks good. So we'll copy this one, turn this to t value. I see. Ask, so, okay. Yes. Well, it's not exactly unique. Output was true. I think there's got to be a way to make this sum unique. Let's just say, because A would be 1 and C would be 2. No, C would be 3. That equals 4, but B is 2. So if you did 4 divided by 3 gives you 1. No, 4 divided by 3. 4 divided by 3 gives you 0.75 divided by 1, 0.75. You get 4 divided by 2 to get 2. So I think addition isn't a unique. Addition isn't. So you can do 3 plus 4 plus 5. And you get the same answer as 5 plus 4 plus 3. I think that's the commutative property. We need something that's not commutative, but they're not sorted. This is opposed to sorting. So it looks like can't really do this version. So we just do the map version. So you'd have a map, call it smap equals new map, and it just maps strings to numbers because it's going to map a letter to the number of occurrences. Now I have to create a map for the values of s. We iterate over car of s. The value would be if the map has already an occurrence for the car, then we'll get it. Otherwise, we'll default to 0. And we'll do smap.set the car value plus 1. Then we can iterate over t, check if value exists in smap. We could, if they do, we decrement the occurrences, and then we just have to validate the remainder of the map afterwards. Date smap occurrences all equals 0, because if they're anagrams, then a map of cat, which would be C1, A1, T1, and tac would produce this map up here. And then if we iterate through the map and subtract letters we come across, the resulting map should be changed from 111 to 000. So if we do for const car of t, and we'll say if smap.has car then we're going to get the value. We do smap.get car, and then we'll check if value minus 1 is less than 0. Then we'll just do smap.delete car. Otherwise, we'll do smap. Or I think it's actually simpler if you just do check if value exists in smap. You just say if smap.has t, and we just do smap.set car of map.smap.get value of car minus 1, right? And if a value ever doesn't exist in the map, we can automatically return false. So now we have to check if any of the occurrences in the map doesn't equal 0. So to do that, we could just do for const occurrences of smap. I don't think you need the entries. If occurrences does not equal 0, return false. If we make it all the way here, we just return true. Our output was false. Oop. smap.has car. So this looks good. I think the solution is a little ghetto. I think you could combine the map validation into this iteration of t. So you'd say, we just get the value, we just say map.get value for car, right? And if car, then you just want to set the map equal to value minus 1. and if the value doesn't exist, you return false. At the same time, if value minus 1 is less than 0, is less than or equal to 0, then you just do s.map delete car. No, actually, you still have to do that step. Still have to do that step. Actually, I think it's an even better solution if you keep the value minus 1, and you could just iterate over occurrences of smap. You have a variable count which equals 0, and you do count plus equal occurrences. At the end, CT does not equal 0, and you don't have an anagram. I mean, if CT equals 0, then you have an anagram. No, because you could have a scenario where you have -1 and so on. I think this one technically counts as a pass, but it's not very. I'm trying to find a cleaner solution. Maybe the best you can do is just create the map, remove values from the map based off t, and then you just validate the map to see that all the occurrences equal 0. Maybe that's the best you can do for this. Also the sorting solution and log n. I think this is the time complexity for this is O of n, but it doesn't seem to be true because you have to iterate over both the length of s and t, so I feel like the time complexity is actually s plus t. Google enough takeaway from this problem. Validating maps is simple. Notice that when you have to remove a value from that when it equals 0, the code can get a little unclean. The takeaway is that using a map for lowercase English letters is constant time, since no matter for any arbitrarily large S or T, will only ever use 26 keys. The takeaway is that when we're accounting for lowercase English letters or capital English letters, you can always just use an array with the character minus the ASCII value instead of the map. So I would say that's a pass. Oh, I forgot to do these two problems. So actually I'll do 10 minutes on just one of them. Do reverse string. Write a function that reverses a string. The input string is given as an array of characters S. We must do this by modifying the input array in place with constant memory. So HELLO, and you have to change it to OLLEH. With Hannah, you have to return it. Reverse with Hannah. It looks like it can be lowercase or uppercase characters. So you can just do this with the two-pointer method. You don't actually have to return anything, so S is going to be handled by reference. Two-pointer method just means that we're going to start left-hand side of the first index that we can start at, and the right-hand side should be the length of the array minus 1. And you want to iterate while left is less than right, because we're going to be swapping characters. So once we reach the midpoint, we'll have swapped all the characters. So we just have to save S sub left. Sub left. And since we're saving S sub left, we want to set it equal to S sub right. And since we overrid S sub left, we can set it equal to temp, and left progress step would be plus equals 1. Rights will be minus equal 1. So this would be for a string with n items. We would reverse it with n over 2 operations, but we'll drop the constant, so it'll just be n. So palindrome permutation. Given a string S, return true if a permutation of the string could form a palindrome. Permutation of the string could form a palindrome. So we have CODE, and there's no matter how you rearrange this won't form a palindrome. If you have AAB, you could rearrange it to form a palindrome. You could put B in the middle, which makes sense. For char rack, this is a palindrome. The length can be up to 5,000 characters. There's always at least one character. S consists of only lowercase English letters. So I think this question is basically asking us to get to the intuition behind what makes something a palindrome structurally. And what that means is that a palindrome structurally can only have two cases. Can either have an even number of characters or an odd number of characters. When it has an even number of characters, we should have 2 pairs for every character. So if we have even number of characters, it's for it to be a palindrome in any order. We could have ABAB. For it to be a palindrome, we have to have 2 pairs of every letter. When it's odd, so we have ABABA, we have A equals 3, B equals 2, and what this means is you have a buffer of one letter being odd. So you can have A equals 3, right, or B equals 2, and the extra A will go in the center, or you can have a equals 2 and b equals 3, and the extra b could go in the center. But you can't have another character that is also odd, like c equals 1, so it can't go in the center. But you can have basically any number of, you can have any number of keys that all have even occurrences, but you can only have one key that has an odd number of occurrences. The way you would solve this is just by loading all of the keys into a map. All the strings into a map. And we could do for const char of s value equals if the map has the character, then we'll get the occurrences for that character, otherwise we'll return 0. Then we set the maps character to value plus 1. Then we can have another variable ct, and this is where we'll validate the map. So we have the letter, the occurrence of the map, and we're just going to do ct plus equals occurrences mod 2, and we can permute a palindrome if ct is less than or equal to 1. So what does that mean? We have CODE, right? In a map that would be C1, O1, D1, E1. Since that's the case, we would validate the map by iterating over the letters and the occurrences. We actually don't need the letter. We'd have the occurrences. We would just name awk. We would have awk mod 2, and that's to say we're basically checking if a number is odd. Now, if it's even, it doesn't change the count at all, right? But if it's odd, what we'll see is that 1 mod 2 gives us 1, O mod 2 gives us 1, 1 mod 2 again gives us 1, and E, which is 1, mod 2 gives us 1. So CT equals 4, which means we have 4 counts of odd numbers. In AAB, our map would be A equals 2 and B equals 1. In the first case, A, which is 2 mod 2, would be CT plus equals 0, and B equals 1 would be B, which is 1 mod 2, which would be 1. We know we're allowed at least one odd letter. Same thing for charac. We have 2, which would evaluate to 0, 2 A's, which would be 0, 2 R's, which would be 0, and 1 E, which would equal 1. So that looks good. Ah, the set is clever. So we load everything into the set, and if we have an even number of occurrences, we should enter the set, exit the set, enter the set, exit the set, and we should only have one element in the set remaining if it's a palindrome. So do insert interval. So you have insert, you have interval, which is a matrix of numbers, and new interval, which returns a number as well, a matrix of numbers. So you're given an array of non-overlapping intervals, where interval sub I equals start sub I, end sub I, represent the start and end of the ith interval, representing where interval sub I equals start sub I, comma end sub I, represent the start and end of the ith interval, which makes sense. And intervals is sorted in ascending order by starts of I. Okay. You're also given an interval start, comma, end that represents the start and end of another interval. Insert new interval into intervals such that intervals is still sorted in ascending order by starts of I, and intervals does not have any overlapping intervals. Merge overlapping intervals if necessary. Return intervals after insertion. So saying the intervals is sorted by the start of the intervals. We can see that 1 is less than 6. And they want us to insert a new interval 2, 5, which presumably would go after 1, 3 because it's sorted by starts of I. But then that would create a case where we can merge 1, 3, and 2, 5. So these get merged into 1, 5, 6, 9. The interval's 4a, which probably goes here, which ends up allowing 3, 5, 4, 8, 6, 7, and 8, 10 to be merged into 3 to 10. Intervals doesn't always have a value. Intervals, when it does have value, always has 2 values in it. Intervals is sorted in ascending order. The new interval always has 2 numbers in it, which is good. And start and end can be from 0 to 10 to the 5. So what we could do, insert the new interval into intervals, then merge overlapping intervals, return overlapping intervals. So how would you insert the new interval into intervals? You could just pretend it's an array of numbers like this, since we're only considering the first number, and we want to insert, let's just say, 3.5. So we would check that while the number we want to insert 3.5 is greater than the current number, then we'll increment that value. So we go to 1, the next one, 3.5 is greater than 2, then go to 3, 3.5 is greater than 3, then we go to 4, 3.5 is not greater than 4, so we place it in 1, index 4. The one problem that makes it a little complicated is that interval cannot have a value in it. So our insert, it'd be cool if our insert would not care if the interval is empty. So we could say basically have 2 branches here, and it's if intervals.length equals 0, then we just say that merged equals an empty array. If it equals 0, then we just say merged equals new interval. And there'll be no need to insert the new interval into intervals. And then otherwise, you want to insert new interval into intervals. And so how do we do that? We just need to find the new index, which would start at 0. And like we said earlier, we'd make sure that while new interval sub 0 is greater than intervals sub new IDX, right, sub 0, then we want to do new IDX plus equal 1, and then we would place intervals splice. We would take the original intervals you take we could say merged equals intervals dot splice, or that slice going from 0 to new idx minus 1. So in the case we have 1, 3, 4, 5, 6, and we wanted to insert 3.5, we'd get to 4. Or I would say intervals dot slice from 0 up to 3. Right, spread that into the array. Then we would say new interval. And then we would say intervals dot slice new index going to intervals dot length. And so I just want to print merged, and then we'll just return intervals just to see if that insertion makes sense. Oh man. So we're given 0, 1, and where is 0, 1 placed? Right, so 0, 1 should have been placed at the front, but it's not placed at the front. It's being placed at this index for some reason. So we're saying while new interval sub 0, which would be 0, while 0 is greater than 2, 0 is not greater than 2, so merge intervals dot slice from 0 to 0 minus 1, which would be no elements. Then we'd put new interval and then slice from 2, 3, 4, 5, 8, 9. Same spot we got stuck at before. For some reason, we don't know how to insert an element into an array. So using slice is strange. Maybe we'll just do something like this case, merged equals copy of intervals. And then we'll just do merge dot splice, right, at the new index minus 1. We want to place, we don't want to delete anything. We want to place new interval. I spelled splice wrong. So 0, 1 still ends up in the incorrect spot. Let me just see what new index ends up being. New index ends up being 0, so new index minus 1. I see, I think -1 ends up actually meaning one element before the last element in the array. I think what we need to do is just say if new index minus 1 is less than 0, then just make it 0. Otherwise, you can use new index. So this looks good. Now we can finally merge the overlapping intervals. So we can merge the overlapping intervals is, or I guess I shouldn't call this merge, we'll just call this INTVS, which is just, or just call it copy, and the copy is basically saying that this is ready to be used. Then we'll create merge, which is going to start with copy sub 0 as the original value. And the way we'll merge is we'll always just continually check if the current interval we're at is less than, if the current, where the current interval starts is less than where the last interval ended, then we want to merge them. So it looks like from 2, 3, 4, 5, right? Once we get to 2, 3, all right, they expected 0, 1, 2. This isn't a good example because we actually end up getting the correct answer, but it doesn't really count. But basically we just iterate over and check if the current interval start ends after, if the current interval starts before the last interval ends, then we'll merge them. Do that, we'll just do const interval of copy, and we'll just say if interval sub 0 is less than or equal to merged, right? And we're going to get the last element in merged. And then we want to merge them to overlap them. And so we would say merged, submerged dot length minus 1 sub 1 equals math dot max of both sub 1 and merge submerged dot length minus 1 sub 1. So I'll change the test case just to be something like 1 to 3. See what we get. I think we get the wrong answer because ours does not actually merge. Oh, I didn't even poof. Otherwise, right, if that's not the case, then we just, if there's no merging, we just want to push it on to the merged array. So we just say merged dot push interval. Somehow we get the correct answer. I think there's an edge case though. If we do, so 0, 1 ends up here. Let's just say if we had 1, 3, so we had 1, 3, no, it doesn't work if they're always sorted. So honestly, let's see if this works. So intervals, otherwise, let's say new interval sub 0 is greater than new index, which starts at 0, and we know that there's at least one element in it. Well, we know there's at least one element in it. So that's kind of strange. While new interval sub 0 is greater than intervals sub new index, which starts at 0, and index 0 should be 1, 5, the 0th element should be 1. Alright, if I'm confused, new interval exists, and we know that intervals exist, but it's saying that for the 0, oh, it's on the next iteration. On the next iteration. Yeah, inserting elements into an array. Very ghetto. Greedy algorithms usually like find a number of something, do something, or find a maximum of something. Is to pick the locally optimal move at each step that will lead to the globally optimal solution. And log in time complexity consists of 2 parts. Figure out how to sort the input data and log in time. Be done directly by sorting or indirectly by heap usage. Please note that in case of well-sorted input, we have returned. The solution was a little bit ghetto. I think the inserting elements into an array, I don't know why that's so complicated. There's element, I don't understand why it's so complicated. It has to be an algorithm that doesn't have to be like, oh, if it's empty, then okay, just set it equal to the value. Otherwise, you have to insert in. I think I just don't know how to use splice correctly, because then I have to use a special thing where, like, if the index is less than 1, then use 0 index. Otherwise, just give it the new index. So it's just a little frustrating. I know we could just, that's why we could have just added it to the array and then just sorted it. That would have been n log n linear time, but if you insert it manually, maybe it's, yeah, if you insert it manually, I think it's linear time then. This is interesting. I think the commenter put it best. This is not, it's just not an elegant solution. Mine is not an elegant solution. But this one is, I mean, actually this one looks kind of involved. There's a lot of math.maxes and sub branches. So maybe it's fine. I would count this as doing this problem correctly. But I think I would opt for the n log n solution rather than I would offer the n log n solution because it's easier to understand, I think. That being said, there's no reason to have this timer. Since there's only I'll just set it back to 20 and we'll start it and we'll do Lru Cache. It's been so long since I tried this problem. I've been avoiding it because I don't really know what I'm doing. But design a data structure that follows the constraints of a least recently used cache. Implement the Lru Cache class, Lru Cache int capacity. Initialize the Lru Cache with positive size capacity. So they want us to initialize with positive size capacity. Then we have get int key, return the value of the key if it exists, otherwise return -1. Update the value of the key if the key exists, otherwise add the key value pair to the cache. If the number of keys exceeds the capacity from this operation, evict the least recently used key. Get and put must each run in constant average time complexity. So the example, just to make sure I'm understanding, you would have input, Lru Cache, put, get. So you'd have a capacity of 2, we'd put 1, 1, and 2, 2. So the key is 2, and the value is 2, and the key is 1, and the value is 1. Then we'd try to get 1, and it does exist, so we'd return 1. Then we tried to put 3, 3, in which case we should evict 2. Right, Lru key was 2, evicts key 2. Cache is now 1, 1 equals 3, 3. Then we get 2, we return -1, right, because it was evicted. And then we put 4, 4, Lru key was 1. Makes sense because we just pushed 3, 3. Evicts key cache is 4, 4, 4, and 3, 3. Then we try and get the key for 1. It's not there because it was evicted because we passed capacity. We get 3, we return 3, get 4, we return 4. Capacity would always at least be 1. Keys can go from 0 to 10 to the 4, and the values for the keys can go from 0 to 10 to the 5th. Most 2 to the 10 to the 5. At most 2 times 10 to the 5th calls we made to get and put. So I think this could be solved with a combination of a linked list, a doubly linked list, and a map or a hash map. The idea being that the linked list allows us to see what key was least recently used, and the hash map allows us basically constant time access into where we would like to be within the linked list. So if we have to return a key or get a key, we can use the map to return that value instantaneously. Then we want to put the key, get and put also modify the LRU property, because if you get or put something, then it is no longer the least recently used, and that's what the doubly linked list would represent. The element at the front would represent the least recently used item. And so if we can push, if we can get the element at the front, we can remove it from the map if the capacity goes over, well, if this put pushes us over capacity. That being said, we would need a map and a doubly linked list. I think the reason we need a linked list is that it simplifies adding and removing. So we could have a map, which we would just say equals new map of number to a D-link node, and we would have a head, which would equal new d-link node, or we could actually just say head, which equals null, but would be of type d-link node, and tail, which would be of type d-link node. And then up here we could declare this d-link node class. You could say d-link node and it would take a constructor. For the constructor, before the constructor would have basically 3 values. It would have the value, which seems to be a number, right, which will just default to 0. We'd have next, which would be a d-link node or null, which would start at null. We'll duplicate this line, which would duplicate this line and make it duplicate this line and make it prev. And then our constructor could take a value, which would be optional. No, the value would not be optional. Actually, the value would be optional. Number should equal 0, prev, which should be a d-link node, or null, which would equal null, and next, which would be a d-link node, or null, which would equal null. Or we would just say this dot value equals value, this dot prev equals prev, this dot next equals next, and we probably don't want it to be null. Actually, null is probably fine. So I'll just run it just to make sure that my class declaration so far for d-link node makes sense. It says a comma was expected. Parameter declaration expected, line 5. So this should be equals 0. This should be a type. And we'll just return 0 to get rid of all of these type issues. And you're not supposed to return anything here. Okay, so we're good to start. In the constructor, when we get a capacity, we'll just save that value under capacity, right, which will start at 0, and we'll say this dot capacity equals capacity. To have our capacity, we also want to set up our 2 head and tail pointers. So we would create head equals a new d-link node, right, and we don't need to pass in anything here. That tail equals new d-link node, right? We want to say head dot next equals tail, tail dot prev equals head, and both prev for head and tail and next for tail will be null, so these are set up, right? And we also want some simpler functions, right? So we want to be able to add a node to this linked list, right? And we'll just say it's the head pointer, and it's going to be d-link node, and we're going to have a node which is also going to be a d-link node, and this is not going to return anything, and this is just going to allow us to add a node to the linked list. So how do you add a node, right? We have pointers pointing to, we have the head node, right? So when we add a node, we want to add a node to the end of the linked list. So the way I would do that is with tail, right? So to add a node to the end of the linked list, actually when we add a node, we'll just add it to the head. We'll use it like a queue, add it to the front. So to add a node, we could say head. We probably want to hold on to next, which would be head dot next, right? And then we want to say head dot next now equals head dot next now equals this current node, right? We want this current nodes dot previous to equal head, so those first two things are lined up together. Problem now being that head connects to this new node, and nodes previous connects, the new node's previous now connects to head, but the node that used to be connected to head now needs to point previously to this current node, and the current node needs to point to that. So we would say node dot next actually equals next, and next dot pre equals node. So this makes sense to me. And then we can also have a function remove node, right? And I think we only need a reference to the node because it's a doubly linked list. We have delinked node void. How do we remove a node when we have pointers connected to the front and the back? So we visualize this as 1 goes to 2, 2 goes to 3. Given a pointer to 2, to remove 2, I think we want to keep a temporary pointer to node dot next. And we'll keep another one to previous node dot previous. And I think what we want to do is just say previous dot next equals next. Previous dot next equals next. Equals next. And then I think what we also want to do is say next dot previous equals previous, thus kind of skipping 2. So we'd say previous dot next equals next. I would remove this arrow to 2, and then we would say next dot previous would now just go all the way back to 1. So that looks good. So to get a key, basically have to check, right, if the key exists, right? So how do we check if the key exists? And I'm just going to run it again just to make sure that my code doesn't have any obvious errors. Line 35. Make sure to use this every single time. So we're good. We want to get a key, we have to make sure it exists in the map, right? So say if map.has, we can't say map, if this.map has the key, right, then we want to return this.map. And the map actually corresponds to a node, which is perfectly fine. So we'll say this.map.get key dot value. That's what we called it. So we can return that. Well, we want to return that, right? But a get actually counts for the LRU mechanism, right? So the elements that were most recently used are going to be at the front of the linked list, right? So to do that, we could just call remove node, right? Which would remove a node from where it currently is. So we could just get the node dot get key. Right, we want to remove the node. We'll still have a reference, so we want to remove it from the linked list, from the doubly linked list, right? Then you want to add node, right? The add node automatically adds it to the front, right? So we would pass in this dot head, right, and node, and then to return the value, we would just say node dot value. At the same time, if the map doesn't have it, we'll just return -1. So let's run that so far, see if that makes sense. So this is put is where the secret sauce comes in. So get is constant time still. Update the value of the key if it exists, right? Otherwise, add the key value pair to the cache. Right, so update the value if the key exists. We'll say if this.map.has key, and we can always just do const node equals this.map.get key. That way we have a reference to it. Just say if node, which means it had the key, right? What do we want to do? We want to update the value of the key if it exists. So we'll say node.value equals value, right? That being the case, though, since we updated it, otherwise, all right, update it, right? So otherwise, right, then add the key value pair to the cache, right? So to add it to the cache, what would we do? We would create a new node, right? A new d-link node. It would get the value of value, and it wouldn't have a next or a previous, right? And we'd say map.set key to this new node, right? And then we don't want to add it to the list yet, because if we do, then we will actually have trouble removing the least recently used key. We'll check right now. If map.size is greater than this dot, and we'll actually do this dot capacity plus equals 1. If map.size is greater than this dot capacity, it means that we're over the capacity. So we have to evict the least recently used key. To do that, we have to get the node at the end, because the node at the front, nodes get set back to the front when they're accessed. And actually, if we update the value, we want to do the same for here as well. We'd remove the node and then add it again. But the least recently used value would actually be at the end. So the LRU would actually be this dot tail dot previous. And we'd say this dot capacity minus equal 1. And we basically want to evict this node, so we'd say remove node LRU. And we don't have to worry about any of these being null here, since head and tail always exist. And then you could add this new node, and I think we would be good. Always forget, have to do this. Add node, we want to add it to the front, right? Oh, so we removed the node, we didn't remove it from the map, so that is a problem. I'm going to say this dot map dot delete. So yeah, the d-link node is also going to have to store the key, because we need a way to get to the map, to the value in the map from the key, to the value in the map from the linked list. So we'd say key number equals 0. And we'll just put this up here. We'll say this dot key equals key, and we'll say key number equals 0. And so when we add the value, we'll say key and value for d-link node and then here we want to delete the key. Oh no, we want to delete LRU.key. Oh man, we're so close. New node. Null, 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 1. So I think we're good. We put, and then we get the value up for 1, so get works. Then we put 4, 4. Then we put 3, 3, and then we try and get, so confused. We do put, get. We get 1, it exists. Then we put 3, 3, right? That should evict 2, and then we get 2, and it should return -1, but it doesn't. At the end of the day, 2 still exists in the map. This.map.set key to this new node, and we increase the capacity. If the size is greater than capacity, we should say booting LRU.key. So it doesn't even seem like it's booting anything, because I don't even get the output. So I'm thinking that maybe I'm just gonna console.log this.map.size and this.capacity to see what's going on here. So we have 1, 3, 2, 4, 3, 5. Oh god, if you don't want to add to capacity, capacity is a set value. The map.size automatically handles our capacity. No way. Sheesh. All right, this is a crazy runtime. Literally 2-second runtime. Let me try it again. Maybe my version is just very slow. Yeah, my version is just dummy slow. It's kind of crazy. I wonder why that is, though. It's pretty fast, though. I mean, it should be constant time. Oh, it's probably because I'm printing so much. Print time takes away a lot. That's better. 886 is not the worst thing in the world. God, oh my God. Now that's satisfying right there. That is it. Yeah, this is just a lot. This one is indeed a lot. Time complexity is constant time for both put and get, and the space complexity depends on the size of the capacity. We're asked to implement this structure, which provides the following operations in constant time. Get the key, check if the key exists, put the key, complete the first added key. The first two operations in constant time are provided by the standard hash map, and the last one by linked list. We could skip this one. Let's do hash. The only we did was hash map plus double linked list. The extended version of the article published on the discuss forum. This problem can be solved with a hash map that keeps track of the keys that maps actually to the linked list node values. The results in constant time for both put and get operation and allows to remove the first added node in constant time as well. One advantage of the doubly linked list is that the node can remove itself without other references. In addition, it takes constant time to add or remove nodes from head or tail. In particular about double linked list implementation here is that there are pseudo head and pseudo tail to mark the boundary, so that we don't need to check the null node during the updates. Yeah, that's what I was trying to say. We always have head and tail, so we don't have to check null during the update. So they have pop tail. So pop the tail, you just do self.tail.previous and then remove the node. So the way we did that was just remove node. So they have the cache, which is the, I assume, the map, size, capacity. Create two delinked nodes. You get, if the node exists, that's great. If not, node return -1. Otherwise, move the access node to the head and return the node value. We did something very similar. Put if not node, the node doesn't exist, we create it, set the keys and the values, add it to the map, we add the node to the front. Oh, that's what they did. I see. I kept removing nodes to just use them in particular instances, but they fused them to increase readability. To add the node, and if self.size is greater than self.capacity, and they pop the tail. Tail equals self.pop tail, and delete self.cache and decrement the size. Otherwise, they update the value and move it back to the front. That is oddly satisfying. That is oddly satisfying. I appreciate people tuning in. Leave a comment if you're doing your own thing. If we can share in our misery. And yeah, that was a good problem, and I'll see you guys tomorrow for another day and another dollop of misery. Actually, it's not misery. The problems are fun. I'm gonna keep it a buck, but yeah, I'll be back tomorrow for the grind. So